Okay, so, good day, good afternoon, good morning, good afternoon, whenever you're watching this. Look at y equals e to the x, and y equals the natural log of x. Okay, y equals e to the x, this one, y equals the natural log of x is this one. So, what do we notice about them? How are they related? Hopefully, since we just left our little unit on, what was that on? Oh, on inverses. You might think these could be inverses of each other. If I were to draw in the dotted line y equals x, 10, it would look like they're folded right over each other. So they are indeed inverses of each other. Each function is the inverse of the other. So what does that mean? What do they do to each other? Well, they undo each other. What one does, if they're truly inverses, if I take the natural log of e to the x, I should get x. And if I raise e to the natural log of x, I should get x. Okay? This is really asking e raised to what power equals e raised to the power that it needs to be raised to get it to the x power, and the answer's got to be x. And this is saying e raised to what power equals e to the x power. And that's got to be x. Okay? So they undo each other. They are inverses, and so that's good. We use that to solve some simple problems about using natural logs and e's and things like that. So if I want to know if the equation of 7 is equal to e to the x plus 1, how do I go about solving it? I use the powers of logarithms to make it all work out. So I take the natural log of both sides. I can do that because if I do to one side, I do to the other, it all works out for the good. So the natural log of 7 is just some number, which is fine. The natural log of e to the x plus 1 is just x plus 1 because the natural log undoes what the e does. So I've got that. And then I can solve that and say that x is equal to the natural log of 7 minus 1. Okay, whatever that is, we can calculate it if we needed an exact answer, but if we're fine, or if we needed an approximate answer, because this is an exact answer. But otherwise, we're good. Okay. If I have the natural log of 2x minus 3 equals 5, how do I undo the natural log? With e. So I go e to the and e to the. Being a little lazy here, not rewriting it, but it'll be okay. E to the natural log 2x minus 3. The e undoes the natural log, and so I'm just left with 2x minus 3 equals e to the 5th. And again, that's some number we could get if we needed to. For right now, we're just going to solve with leaving it as e to the 5th plus 3, and then x is e to the 5th plus 3, all divided by 2. Okay? And if we wanted a decimal number, we could turn it into a decimal number. It's fine. It's good. It's delightful. Okay, so we can use the fact of inverses to solve some equations. So what do we notice about e? What do we notice about e? What's its domain? Domain appears to be all real numbers. We can't see it, but it continues and continues along. So all real numbers. Its range is to be y is greater than 0. It's hard. Y is greater than 0. Okay. What else do we notice about this function? It's an increasing function. Must be monotonic, right? Because it's got an inverse. So it's increasing. Let's see, it opens concave up. That must mean that its second derivative is positive, right? First derivative must be positive as well. Okay, it's an increasing function. It's concave up. It looks like it's got a y-intercept at 1, and doesn't appear to have any x-intercept. So there's that. Because it's an e, it's an exponent. It's an exponential function. We can treat it, if it behaves like an exponent. E to the a times e to the b. We can add the exponents. E to the a divided by e to the b is e to the a minus b. So those are some properties of a good friend. So the derivative of e to the x is e to the x. How can that be? Yeah, now, trust me. The derivative of e to the x is e to the x. So the way we would look at it is the derivative of, with respect to x, of e to anything is e to the u, e prime. Okay, chain rule. Chain rule. So, I made you wait long enough. Why is that the case? Well, we know that the natural log of e to the x is x. So, right, because they undo each other. So what we're going to do is we're going to take the derivative of this side, and we're going to take the derivative of this side. Okay? The derivative with respect to x of x is 1. That's the easy side. The derivative of the natural log of something is just u primed over u. So the u part is e to the x, and the u primed is just the derivative of e to the x. Right? So if I solve this, I get that the derivative of e to the x, if I multiply both sides by e to the x, is 1 times e to the x, or e to the x. So e to the x is its own derivative. Okay? I tend to refer to that sometimes. It's its own grandpa. Okay, there's a little YouTube thing. You can just search for it. You can't really click on this, but and I would if we had the time, but it would make this thing take forever because we'd have to load that and load this. But look it up on the internet. Okay, it's its own grandpa. Okay, maybe we'll watch it in class tomorrow. Remind me. Yeah, the derivative of e to the x is e to the x, which makes it kind of cool. So if I want to know what the derivative of e to the 2x minus 1 is, it's e to the 2x minus 1. But chain rule says don't forget to take the derivative of 2x minus 1, which is 2. Okay, we can get a little more fancy. We can say, oh, what's the derivative of e to the negative 3 over x? Not going to be fooled by that because we know that that's 3x, negative 3x to the negative 1. So the derivative of e to the negative 3x to the negative 1 is e to the negative 3x to the negative 1 times the derivative of negative 3x to the negative 1, which is going to be what? Positive 3x to the negative 2. So 3x to the negative 2. This is what y primed is. So if we were to make this all look nice, let's see, we would end up with something like 3e to the negative 3 over x over x. Okay, so that's a little bit odder, but still, the derivative of e to the x is e to the x. And then it makes it so I can do some of my favorite sort of problems ever in the world. Something like e to the sine squared 6x cubed minus 5x, and I can get all my favorite things into one problem. So let's do this. We know the derivative of e to the sine squared 6x cubed minus 5x is e to the sine squared 6x cubed minus 5x times the derivative of sine squared 6x squared minus 5x. And we know that this is one of my favorite things, the PTA thing, right? So it's a power trig argument dealy. So we're going to go 2 sine 6x cubed minus 5x. Then we got to multiply that by the derivative of sine, which is, that's right, cosine 6x cubed minus 5x. And then we've got to multiply that by the derivative of the argument, which is 18x minus 5. Need a widescreen here. Need a bigger TV. Smaller handwriting. Either way. So then we make this look nice by doing a little rewrite to get everything sort of in a nice sort of order. So I would bring the 2 and the 18x x minus 5 up to the front, derivative of that. And then I would probably put, I don't know, I probably might put my sines and my cosines next. Sine of 6x cubed minus 5x, cosine 6x cubed minus 5x. And I might multiply that all by e to the sine squared. What is that? Sine squared of 6x cubed minus 5x. I should be arrested for my handwriting. All right, so that says e to the sine squared, so all of this stuff. Okay, and you could probably even plunk this down here instead. It might look better. Certainly would look better than the way I just wrote it there. Okay, so makes it so with one little problem, I can find out a bunch of stuff. Oh, there's that. Okay, and then there's some assignments for you. Okay, so remember, the derivative of e to the x is e to the x. The derivative of e to the u is e to the u prime. E to the u du dx, something like that. Okay, so have fun with that. We'll see you tomorrow. If you have questions, you should ask. If not, well, you should come up with some questions to ask. Let's go with that. All right, well, anyway, thanks for watching. See you soon. If you have questions. Oh, yeah, we said that already. So, see you tomorrow. Thanks. Hope you learned something.